Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 27, essential mathematics for pharmacokinetics. Today's objectives is to learn how to perform basic algebraic operations of logarithmic and exponential functions, learn how to graph polynomial and other exponential functions, and learn how to determine graphically and algebraically various parameters of especially exponential functions. Now, why is studying essential mathematics that late in the course if these mathematics are so important for you? Well, this is the reason. Most of the schools, the course of pharmaceutical calculations involves only compounding calculations. But there are a few schools out there that they do teach introductory pharmacokinetics calculations in the course of pharmaceutical calculations because they consider it as important to carry out clinical dosage calculations. Okay, the calculations involved in physical pharmacy or pharmaceutics, they are taught later along with the courses usually. So this is the reason why it is necessary for us to teach this chapter here. Now, also, I would like to emphasize that in my experience, most of the problems out there involves reorganizing equations before you actually use your calculator. And we need to make sure that you are able to do that. So please avoid of using your calculator too often. In fact, most of the exercises here, you won't be able to use your final calculator until you reorganize your equation. Solve for the suitable variable first. Okay, so let us start. So the first one here involves standard notation for the following. So obviously here is to make sure that we understand that this is 2 to the square over 5 to the square, which is 4 over 25, as compared to 4 over 5 there, right? Now, any number raised to the exponent of 0 is equal to 1. And this goes back to the properties of exponents. For example, I'm just going to write something here. 2 to the 5 over 2 to the 5. Of course, that's 32 over 32, which is 1. And if I use the properties of exponent to solve this ratio, this is going to be 2 to the 5 times 2 to the negative 5. So I make this denominator or numerator. So I invert the sign here. I change the sign. And that should be equal to 2 to the 5 minus 5, which is 2 to the 0. And of course, 2 to the 0 is 1. So any number to the 0 exponent is 1. All right. Now, e to the first, the reason I've written over here is to make sure that you know how to use your calculator. It is my experience that at early lectures or quizzes, some students are not familiar with their calculator. So please make sure that you're able to calculate e-values on your calculator. Okay, so let's go through example 11.5. Here I'm asking you to solve for the variables, and in this case, in C, I'm giving you t1 is equal to 2. What I will ask you to do that, please do not substitute t1 equals to 2 to the equation prior to solving and reorganizing this equation for t2. It's not a good practice. So I would like you first to solve for the t2 and finally substitute 2 for t1 there and solve it, okay? It's a good practice. Always reorganize your equation for the variable first. Now, the purpose of this exercise is to tell you that it is not always a good idea to simplify variables. So in this case, it is tempting to cancel one of the h, right? Now, if you don't understand the consequences of canceling a variable, please don't do that. In this case, by canceling the one of the h, eventually you are losing one of the solutions. So this equation is actually a parabola versus an equation after you simplify one of the h, which is a line. All right. So it is okay to cancel or to simplify the variables only if you know the consequences of your actions. Now let's now move to the order of operations, and most of us are already familiar. First, you perform algebra in parentheses, then on exponents, then multiplication, division, and finally addition and subtraction. Now, if, for example, also when you have multiple operations at the same level, you should go from left to right, and that's a rule that you could ask the instructor if this is an operation written in an exam. Okay, but if this is written on any of the spreadsheet softwares, for example Excel, that would be interpreted as 3/4 times n. All right, and please try to solve example 11.6. Do not underestimate the difficulty here, and I'm giving you the answer. The way to solve these problems is always to start from the inside out. Again, do not underestimate the difficulty here, and it's something that you cannot use your calculator. You have to do it in your mind, right? Okay. Now let's proceed to the properties of exponents, multiplication and division of exponents. So here we have negative k all of it squared and negative k all of it third. So the negative k squared is equal actually to k squared. So negative squared is positive. But the negative k to the third power is actually negative k to the third. So eventually I'm adding the exponents now. So that would be negative k 2 plus 3, which is negative k to the fifth. Okay, well, here we are. And you may also solve this one, of course, when the denominator becomes numerator, that's going to be plus 3. All right. Raising powers to powers, so now is raising, is not multiplying or dividing, right? So this would be, raising powers to powers would be equal to a multiplication. So x to the third power and all of it to square is going to be x to the 6. So please try to solve this. This one is particularly useful because it is directly applied to pharmacokinetics. And it helps us determine the half-life of a drug, or let's say it helps us determine the concentration of a drug after a certain half-life. So the half-life of a drug, which is written as T half, is defined as the time needed to reach half of its original concentration. What fraction of its original concentration is remaining after 2.6 half-lives? And why do we pay so much attention on half-life? Because most of the dosing intervals out there are determined by the half-life of the drug. It is that important, okay? Now, to solve this problem, we need to generate an equation. We need to come up with an equation. And the best way to come up with an equation is just cite the number of half-lives and see whether there is any relationships. So here, as by definition, if it's one half-life, that means the drug concentration remaining is going to be 1/2, half of it, right? And 1/2 can be written as 1/2 to the first power. Now, after 2 half-lives, I'm going to have concentration remaining 1/2 square, 1/2 times 1/2. After 3 half-lives, it's going to be 1/2 to the third. And after n half-lives, I'm going to have drug concentration remaining 1/2 to the n. Obviously, n here is the number of half-lives, right? Number of half-lives. So now back to our question. After 2.6 half-lives, the concentration of the drug remaining is 1/2 to the 2.6. Carrying out the algebra is 1/6.063, and that's 0.165 or 16.5% of the drug concentration is remaining compared to its initial value. So this is very, very important example, okay? Now, solving system of equations. Here it is also my experience that some of the students are not able to solve a system of equations. They have forgotten how to do that. Let us take a look of this example here. So we have V1 plus V2 is equal to 7. And then I have V1 times C1 plus V2 times C2 is equal to 18. In fact, this goes back to dilution experiments, right? Or alligation alternate if you wish, or the mass balance equation. And I'm giving you C1 and C2. Now, I have two equations here, and initially 4 unknowns, but you know C1 and C2. So in order to solve the system, you have to first substitute the values of C1 and C2 there, and then solve the first equation for V1 or V2, and then substitute the result on the second equation. So this is what I did over here. Okay? Please try to hide the solution and practice it yourself. But again, unlike the example we solved before, in this case, in order to be able to solve the system, you first have to substitute C1 and C2 in this equation. So you can have two equations and only two unknowns. So now, graphing equations of the form y equals to mx plus b. So this is a line, this is a linear equation. Okay? The slope is m and the y-intercept is b. So if you have an equation y equals to minus 2x plus 3, the slope will be equal to minus 2, and of course the y-intercept is equal to 3. Now, let's start with the y-intercept. If this is related to concentration kinetics of drugs in our body, the initial concentration at 0 time will be equal to 3, because the y-intercept is the value of the y when x is equal to 0. Okay? And you can see there that is equal to 3. Now, the slope, which in this case is -2, is actually the rate of reduction of drug concentration in the body, let's say. And the purpose of this example here is to make sure that you understand how to determine slopes. So let's say if you are given the best fit equation, that's simple. This is your slope, -2. Not +2, -2, okay? And that's the y-intercept there. What if you're not given the equation, but you are given the table? Can you determine the slope based on this data over here, on the x and y? And the answer is yes. So this is my equation for the slope. Let us use any 2 points here, will give you the same answer. Just make sure that you don't change the signs of these numbers, okay? So let us use the first 2 points. So when x is -2, y is 7. When x is -1, I have 5, y equals to 5. So I'm using these 2 points here. Okay? All right. In fact, I should be having one more here. So there is one more over there which is not plotted. Okay, so -2 here. Okay, so I'm using the slope there. That's equal to y2 minus y1. Let's say y2 is 5 and y1 is 7. And now make sure you keep the pairs correctly. So x2 is -1 and x1 is -2. So minus -2. So that would be -2 over 1, and that would be -2. Okay? Don't change the sign, please. That shows the profile of the drug kinetics. So the concentration of the drug is reduced in the body. Again, the y-intercept, that's the initial concentration, let's say, in the body at 0 time. Okay? Coming to the properties of logarithms are extremely important in pharmacokinetics. Now, if you have the argument as a multiplication inside the parentheses here, you could actually add the logarithms as it is shown there. If you have an exponent, you can actually bring it up front. Okay? Now, if you have a division, that would be equal to a subtraction of these 2 logarithms. You could also invert the sign if you invert the ratio here. So m over n, make it n over m, and it would be a negative sign there. Now, this is very particularly important that you use a lot in pharmacokinetics. You can simplify it, of course. So this is, if you have the same base as the argument, that's equal to 1. So what I'm saying here is that log of a of a is 1, okay? And because that was raised into an exponent, this went as a coefficient up front here. It became k. Now you have to be very careful here. This k, it goes with a, so the exponent goes with the base, okay? You cannot treat it differently. All right, very, very cautious here. This is the natural logarithm. The ln e is actually the log of e with a base e of e, and of course e to the e is 1, okay? All right, and here we have a ln 2 equals to log of e of 2. I can rewrite this as log of 10 with the argument 2 over log of 10 to the e, log of 2 over log of e, and that's 0.693. You may see this conversion in your books. I would rather use a ln 2 than this approximation here, but it's really up to you. Also, be very, very cautious. You cannot have a negative number as an argument of log. So the log values are only defined for positive x's, for positive arguments. So this is y, this is x, and this is 0. So all the values of logarithm have to involve positive x or positive arguments. Okay? So these negative arguments are impossible. They are undefined. All right, so let us apply some of these rules. So express as a single logarithm ln of 3 over square root of x minus 5 ln 2 plus 3 ln 3. And be very, very careful here. This is not the same as writing ln e to the third equals to ln e to the third. That's not true, okay? So you can just write ln e is equal to 1 times 3, or you can just take this ln of e to the third power, all of it, and of course it's going to be 3. All right, so you have to treat this as a single number. Be very, very cautious here. Okay, solve the following. So here you have to reorganize your equation first in order to identify the variable t. So first, in order to solve this, take the logarithms of both sides. So ln of 100 is equal to ln of e to 0.02 times t. Now this is ln of 10 to the square. And of course that becomes 2 times ln 10. That becomes a coefficient, right? So that's what I have, ln is 1. So eventually I solve for t. T is equal to 2 ln 10 over 0.02, and that's equal to 230. Do you understand my point now of not being able to use your calculator unless you solve or you reorganize your equation first and solve for the variable? This is a routine equation in pharmacokinetics. This is called a first order kinetics. Okay, now what about this one? Log of y equals to 2. I can rewrite this as 10 of log of y is equal to 10 to the 2, and of course y is equal to 10 square, which is 100. Okay, because this log is regular logarithm, they have a base of 10. Okay, now graphing special exponential functions. So this is important because most of the kinetics of drug absorption, distribution, and elimination are routinely approximated by first order kinetics, which resemble this form of exponential equation. Y is equal to a times e to the k times x. Okay, sometimes we have a negative k, a positive k, doesn't matter. A is called the leading coefficient and k is called the coefficient of exponent x, and is commonly the rate of kinetics, the rate constant. Okay, not the rate constant. Okay, now the leading coefficient a indicates the graph's intersection of the x-axis at y equals to 0, at x equals to 0, excuse me, and sometimes this is the initial concentration, which is called C0. Okay, so this is very, very handy because you could curve your data and identify the initial drug concentration when you first, let's say if you have given the dose by an IV bolus, what would be the initial concentration at time 0 in the blood? That should give you the C0. Okay. All right, I think we have discussed this anyway. Okay. Okay, so let us take a look of example 11.2. point 14, which addresses the graphing of a first order equation, c equals to e to the minus 0.2 times t, which is commonly encountered in pharmacokinetics. So here I'm giving some values of the time, and I've used positive, of course, time. Negative time doesn't have a meaning. And for every t here, I determine the concentration. And the question is like to determine the slope and intercept if possible, okay? So here I plotted my data, and graphically I can see that the initial concentration at time equals to 0 is 1, whatever units are there. Now notice that the slope of this curve is of course variable. It changes with time, right? You can see that with increasing time, the slope becomes less steep, more horizontal. Okay? So the slope is not constant, it varies as a function of time, and it can be shown with differential calculus that the slope is actually equal to negative 0.2, and this is the rate constant, times c. So what it tells us is that as the drug concentration becomes smaller and smaller, the rate of elimination of the drug from the body in this case, it also decreases. Okay? So I don't have a constant rate of elimination in this case. I have a variable rate of elimination, but that rate of elimination is described by a rate constant and the concentration of the drug present at the body at particular time periods. Okay, and at this point it's time for the practice exercises. Please try to solve all of them. They are quite simple for you. And that would make you very competent in the essential mathematics for pharmacokinetics. The answers are, as usual, they are given. And here we have one particular exercise that actually refers to the accumulation of drug in the body, or kinetics that is related perhaps to drug release from let's say a control release dosage form. Enjoy. So at this point I would like to thank you for your time. Until next time.